Hello, curious minds. Welcome back to ProjexCellence ProDigy, your one-stop destination where mechanical engineering meets project management. I am Govind, a certified PMP and a mechanical engineering professional with more than 25 years of experience in the power and energy industry. In today's lesson, we are taking an interesting topic: components of reciprocating internal combustion engine. Whenever we see a diesel engine, gas engine, marine engine, or automobile engine, all these engines are made up of several important mechanical components which work together in perfect synchronization. Understanding these components is extremely important because each part has a specific role in supporting combustion, transmitting power, controlling motion, lubrication, cooling, and maintaining engine reliability. As there are many key components in a reciprocating IC engine, so we will continue this topic in the next few lessons. And in today's lesson, we named it Part A. We will be discussing the components: engine block, lube oil sump, crankshaft, connecting rod, piston, cylinder liner, and cylinder head. So let's get started. Engine block. Engine block is called the backbone or the main supporting structure of the internal combustion engine because almost all major engine components are either mounted on it or connected to it. In multi-cylinder engines, all the cylinders are usually cast together as one single unit, which is called the cylinder block. Engine block is generally made of cast iron or alloy steel because these materials provide high strength, good rigidity, excellent wear resistance, and good vibration damping properties. In modern automotive engines, aluminum alloy blocks are commonly used because they are lightweight and help in better heat dissipation. Now let's understand the different sections inside the engine block, which are shown here in these images. This lower portion is called crankcase. We can see it here. And inside the crankcase, the crankshaft is installed and supported on main bearings and main bearing caps. During engine operation, huge combustion forces are transmitted from the piston to the connecting rod and finally to the crankshaft. So naturally, the crankcase has to be very strong and rigid to handle these kind of heavy loads and engine vibrations. Now, if we move upward, this section is called the cam case. And inside the cam case, the camshaft is installed. The camshaft rotates inside cam bushings and controls the opening and closing of inlet and exhaust valves at correct timing. It also guides the fuel tappet and helps in deciding the fuel injection timing. The camshaft gets its drive from the crankshaft through these timing gears or gear train arrangement. Next, these circular openings shown here, these are called cylinder liner pockets or liner bores. Inside these bores, the cylinder liners are fitted. These liner bores must be machined very accurately because even a small misalignment can lead to excessive wear, vibration, or even piston seizure. Now let us come to the main bearing support area. These are the strong support structure provided inside the crankcase for mounting the crankshaft. Crankshaft rotates on main bearings fitted in these supports, which are called saddles and main bearing caps. These supports carry extremely high rotating loads and combustion forces during engine operation. Gear train housing. This section here, this is called the gear train housing. Inside this area, timing gears are installed. These gears transmit rotational motion from the crankshaft to the camshaft and governor. Proper gear alignment is very important because even a small timing error can badly affect the engine performance. Internal lube oil passages. Inside the engine block, there are internal lubricating oil passages, also called oil galleries. Pressurized lube oil flows through these passages and lubricates main bearings, camshaft bearings, cylinder heads, and other moving parts. Similarly, cooling water cavities or water jackets are also provided around the cylinder liner area. Cooling water circulates through these cavities and removes excess heat generated during combustion. Without proper cooling, the engine can overheat and serious damage may occur. And finally, this section is called charge air gallery. In turbocharged engines, compressed air from the turbocharger passes through the charge air cooler and then enters this gallery. And from here, the compressed intake air is distributed to multiple cylinders. So overall, if you observe carefully, the engine block is not just a simple metal structure. It is actually a complete integrated system which contains structural supports, lubrication passages, cooling passages, air passages, and mounting arrangements for major engine components. And that is why the engine block is often called the skeleton or backbone of the reciprocating internal combustion engine. Next component is lube oil sump. If you look at this image, the oil sump is fitted at the very bottom of the engine, just below the crankcase. In simple words, we can say the oil sump acts as the storage tank or reservoir for the engine lube oil. During engine operation, lube oil is continuously circulated to various moving parts like main bearings, connecting rod bearings, camshaft bearings, gear train, cylinder heads, and many other components. And after lubricating these parts, the oil flows back down due to gravity and collects again inside the sump. From there, the oil pump draws the oil once again and sends it back into the lubrication system. And this process continues throughout the engine operation. If we talk about the functions of the oil sump, the main function is to store the lube oil required for the engine. The second function is to collect the returning oil after it has lubricated various engine components. And the third function is to help in cooling the lubricating oil. As the oil remains inside the sump for some time, it transfers part of the heat to the sump body and surrounding atmosphere, which helps reduce oil temperature. Now if we look inside the oil sump, it is designed to store the required quantity of lube oil for the engine. In most of the engines, special plates, which are also called baffle plates, are fitted inside the sump. We can see here. The purpose of these baffles is to prevent the oil from splashing too much. When the engine is vibrating, the vehicle is taking a sharp turn or operating on an inclined surface. Without these baffles, the oil could move away from the oil pump suction pipe for a short time. If that happens, the oil pump may draw air instead of oil, which will result in poor lubrication. The baffle plates help keep the oil around the suction area, ensuring that the oil pump always receives a continuous supply of oil. Another important component inside the lube oil sump is called oil suction strainer. Before the oil enters the oil pump, it passes through the strainer. The strainer prevents large particles, metal chips, or contaminants from entering the lube oil system. Depending on engine design, lube oil systems are generally classified into two types: wet sump system and dry sump system. In a wet sump system, the lube oil is stored directly inside the sump below the crankcase. This is the most common arrangement used in cars, generators, and many industrial engines. In a dry sump system, the lube oil is stored in a separate external oil tank, and only a small amount of oil remains inside the sump. Dry sump systems are commonly used in racing cars, marine engines, and some high performance engines where continuous lubrication is critical. Now let us move to another very important component of the IC engine, which is the crankshaft. The crankshaft is often called the heart of the engine because it converts the up and down movement of the piston into useful rotary motion. As we know, during combustion, high pressure gases push the piston downward, and this force is transmitted from the piston to the connecting rod and then from the connecting rod to the crankshaft. The crankshaft then converts this reciprocating motion into continuous rotational motion, which is finally used to drive a generator, vehicle wheels, marine propeller, pump, or any other driven equipment. Now let us understand the different parts of the crankshaft. First, these portions are called the main journals, and these main journals are supported on the main bearings fitted inside the engine block. These journals support the entire crankshaft and allow it to rotate smoothly inside the engine. A thin film of lube oil is always maintained between the journal and the bearing to reduce friction and wear. Next, these offset portions are called the crank pins. The big end of the connecting rod is mounted on these crank pins. When the piston moves up and down, the connecting rod transfers force to the crank pin. And this is where the actual conversion of reciprocating motion into rotary motion takes place. Now look at these sections connecting the main journals and crank pins. These are called crank webs or crank arms. The crank web transfer combustion forces from the crank pin to the main journals. They have to withstand very high bending and twisting loads during engine operation. Now observe these heavy masses provided on both sides. These are called counterweights here. The purpose of counterweights is to balance the rotating and reciprocating masses of the engine. As pistons and connecting rods move continuously, they create unbalanced forces. Counterweights help reduce these forces and make the engine run more smoothly. Without proper balancing, the engine would experience excessive vibration, increased bearing loads, and reduced component life. Now look at this gear mounted at the end of the crankshaft. We can see it here. This is called the crankshaft gear. The crankshaft gear transmits rotational motion to various engine components through the gear train. It drives the camshaft and the governor. Fastening screws. Fastening screws or bolts provided in a certain locations. And these high strength bolts are used to secure counterweights and other crankshaft components. Crankshaft is not a solid piece of metal. In reality, especially drilled oil passages are provided inside the crankshaft for lubrication purposes. These oil holes play a very important role in supplying lube oil to the rotating bearings. The lube oil pump sends pressurized oil to main bearings mounted inside the engine block. From the main bearings, the oil enters the crankshaft through oil holes provided in the main journals. The oil then travels through internal drilled passages inside the crankshaft and reaches to the crank pins. After lubricating the big end bearing, the oil further travels through passages inside the connecting rod and reach the small end bush and gudgeon pin area. From there, through piston skirt, oil reaches to piston rings for lubrication and the underside of the piston crown, where it absorbs heat and helps keep piston temperature under control. The crankshaft is manufactured in one piece using forged steel or alloy steel. These materials provide high strength, excellent fatigue resistance, and long service life. Connecting rod. Connecting rod connects the piston to the crankshaft. Its main job is to transfer the force from the piston to the crankshaft. When fuel burns inside the cylinder, high pressure pushes the piston downward. This force passes through the connecting rod and reaches the crankshaft. Then the crankshaft converts this up and down motion into rotary motion. If you see the connecting rod parts, the first and foremost part is con rod upper part. This is the main body of connecting rod. It connects the small end and big end and carries heavy tensile and compressive loads. Second is con rod lower part. This is the detachable cap at the bottom side of the connecting rod. It is removed during bearing inspection or replacement. Small end bush. The small end connects to the piston through the gudgeon pin. A bush is fitted here to reduce friction and wear. Big end bearing shells. The big end of connecting rod is mounted on the crankshaft crank pin. Bearing shells are fitted here, so the connecting rod can rotate smoothly on the crank pin with an oil film. Screws and nuts. These hold the lower cap tightly with the connecting rod body. They must be properly tightened because they carry very high dynamic loads. Shim and dowel pins. In 3-piece con rod, shims help in proper adjustment or clearance control. And dowel pins help in accurate alignment of the connecting rod cap with the connecting rod body. Piston. The piston is one of the most important moving parts of the engine because it is the first component that directly receives the force produced during combustion. During engine operation, the piston performs several important functions. It compresses the air or air-fuel mixture during the compression stroke. It receives the high pressure force generated during combustion. It transfers this force to the connecting rod and together with the piston rings, it helps seal the combustion chamber. Now let us understand the different parts of the piston. At the top, we have the piston crown here. The piston crown is the upper part of the piston and it is directly exposed to the combustion process. These groups are called as piston ring groups and the piston rings are fitted inside these groups. The accuracy of these groups is very important because excessive clearance can result in ring wear, blow by and increased oil consumption. The upper rings are called compression rings. Their main function is to seal the combustion chamber and prevent high pressure combustion gases from leaking past the piston. Usually, the top ring experiences the highest temperature and pressure, while the second ring provides additional sealing support. Below the compression rings, we have the oil rings. Its job is to control the amount of lube oil present on the cylinder liner wall. It scrapes excess oil from the liner surface and allows only a thin film to remain there. If oil ring gets failed, oil could enter the combustion chamber, which may result in higher oil consumption and exhaust smoke. The lower portion of the piston is called the piston skirt. We can see here. The piston skirt guides the piston during the up and down movement inside the liner. The skirt also absorbs side thrust forces, which are generated by the angular movement of the connecting rod. Now look at this hole passing through the piston. This is called gudgeon pin bore. The gudgeon pin passes through this bore and connects the piston to the small end of the connecting rod. The gudgeon pin is normally made from hardened alloy steel because it experiences high loads and repeated stresses. In heavy-duty engines, the piston contains internal cooling spaces or cooling galleries. Lube oil is directed through these galleries to remove heat from the piston crown. This helps prevent overheating and increases piston life. For light-duty engines, pistons are manufactured from alloy steel because it is lightweight and has good heat transfer properties. However, in large marine engines and power plant engines, piston crown is made of forged steel and skirt is made of nodular cast iron. Cylinder liner. A cylinder liner is basically a cylindrical sleeve which is fitted inside the engine block. The piston moves up and down inside this liner throughout the engine operation. So in simple words, we can say the cylinder liner provides the working surface on which the piston and piston rings travel. During engine operation, the liner has to withstand high combustion temperature, high combustion pressure, continuous friction from the piston rings, and constant wear during every engine cycle. That is why the cylinder liner must be strong, accurately machined, and high wear resistant. Cylinder liners are commonly made from cast iron because cast iron provides good wear resistance, good heat transfer properties, and excellent machinability. Based on the cooling arrangement, cylinder liners are generally classified into two types: dry liners and wet liners. In dry liner, the cooling water does not come into direct contact with the liner. The heat generated in the liner is first transferred to the engine block and then from the engine block to the cooling water. The liner we can see here is a dry liner. In this liner, only the collar or upper portion of the liner is cooled through the water jacket arrangement. One major advantage of a dry liner is that there is practically no risk of cooling water mixing with the lubricating oil because the cooling water does not directly surround the liner body. The second type is the wet liner. In a wet liner arrangement, the outer surface of the liner is directly surrounded by cooling water. Because of the direct contact with coolant, heat transfer is much more effective and liner cooling is significantly better. However, there is one disadvantage. If the sealing rings or O-rings fail, cooling water can leak and mix with the lube oil, which may cause serious engine problems. That is why the condition of liner sealing rings is very important in wet liner engines. If you look near the top portion of the liner, here, many large diesel engines and marine engines are provided with an anti-polishing ring. The main purpose of this ring is to remove carbon deposits that build up on the piston top landing area. Anti-polishing ring helps to prevent liner polishing, reduces lube oil consumption, and increases liner service life. Cylinder head. The cylinder head is mounted on top of the engine block and cylinder liner. It closes the cylinder from the top and forms the upper part of the combustion chamber. During engine operation, the cylinder head is exposed to extremely high temperature and pressure generated during combustion. Therefore, it must be strong, accurately machined, and properly cooled. Cylinder heads are commonly manufactured from cast iron or alloy steel because these materials provide high strength and excellent resistance to thermal stresses. If we see here at the center, the injector pocket is casted in cylinder head where injector is fitted. And either side of the injector, we can see the two inlet valves and two exhaust valves. The inlet valves allow fresh air to enter the cylinder during the intake process, and the exhaust valves allow the burnt gases to leave the cylinder after combustion. Now look at the areas where the valve sits when closed. These are called valve seats. The valve seat provides a gas-tight sealing surface between the valve and cylinder head. A properly sealing valve seat is very important because even a small leakage can reduce compression and engine efficiency. The valve stem moves inside a component called the valve guide. The valve guide ensures that the valve moves only in the correct direction and maintains proper alignment during operation. Another important component is valve rotator. The valve rotator slowly rotates the valve every time it opens and closes. This continuous rotation helps distribute the heat evenly around the valve face. It prevents carbon deposits from building up at one location, reduces uneven wear of the valve and valve seat, and ultimately increases valve life. Next, we have the valve springs. The valve springs are fitted around the valve stem, and their main function is to keep the valve normally closed. When the camshaft pushes the valve open, the spring gets compressed. As soon as the cam lobe moves away, the spring expands and forces the valve back onto its seat. In this way, valve springs ensure proper sealing of the combustion chamber and accurate valve operation. Yoke and yoke pins. A yoke is a bridge-like component which is placed between the rocker arm and two valves to ensure that both valves open and close together. And yoke pins guide the yokes. Indicator valve. This is a small valve fitted on the cylinder head which is mainly used for monitoring and diagnostic purpose. It allows operator to measure cylinder pressure and analyze combustion performance. Before starting a large diesel engine, the indicator valves are often kept opened while turning the engine slowly. This helps check whether any water, fuel or lubricating oil has accumulated inside the cylinder. If any liquid is present, it can be expelled safely before starting through indicator cock, which prevents serious engine damage due to hydraulic lock. Next, we have the safety valve, also called as the cylinder relief valve. This is a very important protective device. Under normal conditions, the safety valve remains closed. However, if abnormal cylinder pressure develops due to reasons like pre-ignition, detonation, incorrect combustion or hydraulic lock, the valve automatically opens and releases the excess pressure. Starting air valve. Large diesel engines do not use electric starter motor like automobile engines. They use highly pressurized compressed air for starting. The starting air valve allows the compressed air to enter the cylinder during the starting sequence. The high pressure compressed air pushes the piston downward and helps rotate the crankshaft. As the engine gains speed and fuel combustion starts, the starting air supply is cut off and the starting air valve closes automatically. Cooling water passages. The cylinder head contains internal passages which are known as cooling water passages. Cooling water continuously circulates through these passages and removes heat from critical areas like flame plate, exhaust valve seats, injector surroundings, and the exhaust port region. This cooling is extremely important because the cylinder head is one of the hottest components of the engine. Without proper cooling, overheating can occur, which may lead to cracking, distortion, or gasket failure. So that's all for the today's lesson. As you can see, a reciprocating IC engine consists of many important components, and we have only just started exploring them. In the next lesson, we will continue with more engine components and understand how they work together to make the engine run efficiently. Until then, keep learning and keep exploring. If you found this lesson helpful, please like, share and subscribe to ProjexCellence ProDigy. Thank you for watching. Namaste, goodbye, Sampai Jumpa.